So I think most of you who are on this call today are familiar with who I am, but I'm Marlene Cardin. I'm the Director of Projects at ProSensus, and I've been with the company since 2007, so for quite a while now. What I'll go through today is just a brief introduction to ProSensus and FormuSense. I'll introduce also the demo data we'll be using today, and I will have to give a brief overview of modeling and simulation prior to going into the focus of today's webinar, which is, of course, the optimization features. So we'll be going through our approach in a slide format and then about 15 minutes in FormuSense or so. We will also have time for questions and answers at the end, about 5 minutes, but this is a live webinar that's being recorded, and we'll pause it during the Q&A, as people generally don't seem to like asking questions when they're being recorded. Feel free to send questions to the chat as the meeting progresses, and then, like I said, we will get to them at the end. So just a brief introduction to ProSensus. As many of you know, we were founded by John McGregor after he spent 30 years pioneering kind of MVA at McMaster University and applying that to various manufacturing problems. And we were established nearly 20 years ago now, so quite a while, and we're located near Toronto in Canada. Now, when we talk about doing analytics for manufacturing, we have two main areas in which we work. The one being materials formulation data, which is the focus of today's webinar, and the other being historical process data. So back in 2016, ProSensus sold a software for a process analysis called ProMV to AspenTech, and they've continued to develop that software for kind of process monitoring, troubleshooting, and so on. And we help provide implementation services for them. But for product development, we provide consulting and our own FormuSense software. So our product development experience is actually quite broad. If you look at this slide here, you will see some of our past applications that we've done through food, pharma, oil and gas, chem and polymers. So not only are the industries diverse, but also are the kind of objectives of these problems. So in some cases, we're looking for improving, reformulating to improve quality, while in others, we're looking to reformulate to reduce costs, or even just to avoid experimentation, excessive experimentation, or, you know, in some cases, using more sustainable ingredients and so on. So our experience is quite broad, and we used to do this through custom software and consulting services, but we've now taken the commonalities in all of this diverse examples and created FormuSense, which is a desktop software that users can use to go through this workflow themselves. In this case, when you do this, this has been quite timely in the development of FormuSense as industry has kind of shifted in the last couple of years. As you all know, the world has changed kind of significantly, and companies have hired data scientists to do this type of work and are more hesitant to share data as these new kind of IT security policies and things come into place. So it's quite timely in the fact that our customers can now go through this workflow themselves. So so FormuSense has kind of taken all that experience and developed and allows you guys to implement this proven framework. Here's a screenshot of the software, which shows you the workflow on the left panel here, from going all the way from importing the data through the various framework steps, modeling, simulation, optimization, and so on. So it's a no-code platform that streamlines this workflow. And we kind of have 4 buckets the work falls into. The first one is assembling the data. So we all know when we're doing these types of projects that assembling the data is kind of the most painful part, but also very important to make sure that we can look at that data, make sure there's actually variability in the data, nothing missing, and so on. And then we have a whole tab in the software that allows you to calculate mixture properties and I'll actually be going into a little bit of detail on that in a few slides from now. Once we have a suitable data set, we can build predictive models and interpret those results. It's always important to have tools to be able to learn from that model and verify the correlations found with the subject matter experts, and maybe test the model on some prediction sets and so on. And so that's an important step that we accomplish in the modeling section. And then once we kind of trust our model, we get into the really fun parts of doing the simulation, where we can specify certain formulations and process conditions and see what the software predicts. And then also optimization, which is our feature that was released this June, where we can go back and calculate, kind of back calculate, given some targets and constraints, back calculate that formulation and process condition we're looking for, and so on. So this kind of our introduction to a brief introduction here to FormuSense. And yeah, like I said, this webinar is going to be a little bit brief and focusing heavily on the optimization, but we do have some past webinars on our website from these, like where we go into detail on modeling and simulation, that you're welcome to listen to. And we also provide a 30-day trial with a data set that you can, with the same data set that I'll be using through this workshop, through this webinar, sorry, that you'll be able to go through these steps in more details. We provide tutorial slides and so on. So here is this demo data set that some of you may have seen in the past if you've listened to our past webinars. The objective in this data set is to reformulate existing functional polymers and develop new functional polymers by considering new ingredients. So this process combines 3 different ingredient types or classes of ingredients, rubbers, polypropylenes, and oils, in a relatively simple process to create functional polymers. In the data set, we have 111 existing formulations. We have 11 properties that are measured on the rubbers, so ingredient properties such as molecular weight and so on, and their cost of the rubbers. We have, for polypropylene and oil, we only measure density, and we also have their cost. Now we have about 35 ingredients, so I think there were about 13 rubbers that were used in historical formulations, and about 18 new rubbers that the customer wishes to consider when reformulating these these rubbers, these functional polymers rather. We have four polypropylenes and 1 oil. And also we have 2 process conditions. It's a relatively simple process, and we measure 7 quality properties. So it's really important here, the key concept is that they want to consider new rubbers. So setting up the model in a way to do that is important, and that is done through the inclusion of ingredient properties to quantify those ingredients. And I'll show you that in a bit. First, I'm just going to briefly show you how that data would be set up before importing into FormuSense. And so in our case, the data are loaded from Excel. And what you see here is an Excel spreadsheet with different tabs. The first tab is the formulations tab, where for each formulation, each ingredient is listed that belongs to that formulation. It's mass percent in this case, but it could also be a weight, like a pounds or grams or something like that. And we also list out which ingredient class that ingredient belongs to. And then we can have kind of a family indicator variable that will allow us to do things like coloring and modeling or building submodels and things like this. We also have tabs for each of the ingredient classes that list out the ingredient names and any of their properties and their cost. So we have 3 separate tabs here for the rubbers, oils, and polypropylenes. And then for process conditions, we simply list out the formulation and the mixing speed and temperature that we had at that for that given experiment. And then we can also have these kind of descriptor variables that we can turn into categorical variables or use for coloring and things like this in the model. And then we also have another tab similar to the process conditions, but just for quality, where we list out what the quality was for those formulations. Oops. Okay, so just briefly before getting into details on optimization, I do want to mention the importance of mixture properties. And so mixture properties are advanced input features that can improve the model predictive abilities and allow new unused ingredients to be considered in future formulations. So what we have here is when we have the formulation ratios and for the amount used for each of the ingredients and the ingredient properties, we combine those using mixture rules in order to calculate mixture properties. So generally you can use, for example, the ideal mixing rule, but we have other ones configured in FormuSense for you to try. And while this is important, because when you model with mixture properties rather than with individual ingredient ratios, you can then consider new unused ingredients during simulation and optimization. So while this is important, this is actually generally the most difficult part of gathering these data sets, is having suitable ingredient properties. So we often have hundreds of ingredients and tens of ingredient classes, but typically only a few of the ingredient properties are global. So you might not measure the same things on rubbers, oils, and polypropylenes because certain measurements might not be relevant across the classes. Some classes often have no ingredient properties at all, and in other classes may poorly characterize the mixture. So sometimes we have ingredient properties that are basically the same for each ingredient, and so that way the lack of variability is not really going to be helpful for any type of modeling. So in FormuSense, we try to address these various combinations of ingredient properties we may get, and mixture properties can be calculated either per class or globally. So what that means is, for example, in this case, if you're combining up to 5 different rubbers and you have molecular weight measured on each of them, you can do the ideal mixing rule to just calculate the mixture molecular weight for the rubber class. Or you can, if you had molecular weight measured on all of your different ingredients, you could do it globally across all the classes. Models can also be built with ingredient ratios if you have no properties, and that's very reasonable in some cases if you're not trying to extend to new ingredients. And that works well, and FormuSense allows you to do that. You just can't consider new ingredients when you get to simulation and optimization. So here is the resulting model for this particular example. We have the way that FormuSense would organize this data would be from the rubbers. From this data set, we would have the 2 process conditions for each formulation. And then FormuSense calculates and uses in the model the class ratios. And that is the amount of rubber that's used, the amount of polypropylene and the amount of oil that's used. It sums to 100, but it's nothing on individual ingredients, just kind of the overall amount of each class that's used. And then we've calculated the mixture properties of the rubber using, in this case, the ideal mixing rules. So there were 11 properties. And we've also been able to calculate the global mixture property of density because we have density measured on each of the classes using the ideal mixing rule. And we have the 7 quality properties. So that's kind of how the data is formatted. As you see, there's nothing in here that includes, the model variables do not include individual ratios of ingredients, and therefore you can extend this to new ingredients. I know that might be a little bit to wrap your head around the first time you hear it, but we're obviously happy to answer questions on this if you have questions. And then in FormuSense, you get various modeling tools, various plots to interpret the models. So one of the important ones we use, of course, PLS modeling, is you see the score plot, which is kind of the historical experimental space where you see that each dot is a past formulation, and ones that are close together are similar in both quality and input data. And you also see like areas where you may have gaps, and those gaps might be interesting to investigate, and we will do that later in optimization. We also get model fit for each of the 7 quality metrics. We get the orange bar that's on a trading data set. That's 80% of the data set. The blue here is every 5th formulation excluded. So you can kind of check how well it would extend to data that the model hasn't seen. And then the final model is using 100% of the data. And that's the model that we would then use for simulation and optimization. And there's a variety of tools to interpret the results. Everything's colored by kind of block of data variables, and what we see here is the coefficient plot for predicting quality variable Y5, and we can interpret these bars and understand whether or not this makes sense, that the highest Y5 would be achieved when we have highest mixing temperature, higher amounts of rubber, and higher global density. So that's based on our kind of knowledge of the system. So once we have a model that we can, okay, sorry, that's not what's in this next slide here. So just briefly, MVA advantages and why we use MVA for product development. So by MVA, I mean multivariate analysis and PLS modeling. So one of the big ones is, of course, it's not a black box. There's a lot of intuitive plots to understand the correlations that are being fit. And more recently, as we've attended conferences, we've heard things about interpretable, explainable AI, and really the kind of pressure that manufacturing companies are putting on companies like us to make sure that we're delivering models that they understand what's actually happening with those models. So that's always been a benefit of PLS modeling. It can also handle missing data, typically up to 30%, and correlated variables. So that's important. We often have some missing data, missing ingredient properties type of thing in these examples. And also important is that models can be built on both small and large data sets. So in our use cases, we've seen data sets as small as like 7 past formulations and as large as thousands. And so any modeling method that we use in this tool has to work on both. Can be used for simulation and inverted and numerical optimization. Of course, another important point. And the last one is that there are model validity metrics known as HT2 and SPE in multivariate modeling that help you during model building find outliers and interpret outliers, and during simulation and optimization quantify the degree of extrapolation and avoid extraneous extrapolation. Now, I've only listed advantages here. The main disadvantages of PLS modeling is that it's a linear modeling method. And the way we handle that in FormuSense is that we allow some transformations of variables to kind of linearize a nonlinear, if there's a nonlinear system. And we find that's often good enough, because when our customers work on these types of applications, they're usually working across kind of like a narrow range of data. So for example, if they're working in polymers, they're typically working with one catalyst family or something like that, where the relationships tend to be relatively linear or can be linearized with some simple transformations. So once we have a model that we've built, then we of course get into the really fun stuff, which is simulation and optimization. So in simulation is where you're specifying kind of the input variables, those ingredient selections, the ratios at which they're combined, and the processing conditions, applying the model to see what's predicted. And then in optimization is saying, I want to achieve this type of quality. What are the ingredient selections and ratios to achieve those under given constraints? So that's kind of the key to simulation and optimization. So simulation here is shown, I'm just showing it on a slide rather than showing it in FormuSense, because there's more detail. You can ask for more details if you're interested. But simulation is applying that PLS model in a forward direction to simulate the outcome of those new ingredients and process conditions. So to do these kind of what-if scenarios. The user enters the process conditions and the recipe, hits generate simulations, and in the background, FormuSense calculates mixture properties and the class ratios and applies that model, and then provides visualizations. Now it's very quick. You know, you can configure up to 100 simulations and it'll run, you know, in a couple of seconds. And on the screens, you'll kind of see a score plot of where those scenarios that you've configured fall. Here I've configured 2, what the quality is that's predicted in both tabular and plotting formats, and also how close are you, how much is that set of conditions extrapolating in terms of the 99% HT2 limits and SPE limits, and what the cost of that formulation is. So that's simulation. And then lastly, of course, is optimization. So optimization, constrained optimization is sometimes referred to as the backward direction, although some people kind of argue with that definition. But the goal is really to determine the required ingredient and process combinations that will achieve specified targets under constraints. So any optimization requires an objective function. And we have multiple terms in our objective function, which I've listed out here. The main thing we're trying to minimize is the deviation from configured targets. So the user can target either a location in the score plot or quality targets. And I will show you both once we get into the demo. And then we have some kind of helper terms here to limit extrapolation, minimize the cost, and penalize ingredients that may have missing data. And of course, there are constraints and limits that are configured. The most important one is that you don't want to have a formulation where their ingredient ratios don't sum to 100%. So that's an important one that may seem simple, but actually in FormuSense, we allow the users to build kind of any combination of models. And so that was in the background, that's a little more complex than you might think. We also limit the number of ingredients that we use in a class. We allow the user to turn on and off the availability of certain ingredients. And when an ingredient is used, so non-zero, we make sure that there's a minimum that it's used at. We don't want the software to recommend using a 0.0001% of something when the system can maybe only use 3% of an ingredient, for example. So that's some of the constraints on the ingredients. And then we have upper and lower bounds on process variables that can be configured, mixture properties, and quality variables. And we also have upper limits on how far you can extrapolate in terms of the SPE and HT2, and upper limit for the cost that the optimization can. The optimization is relatively quick. The runtime is less than 3 minutes for today's demo, where we have 40 decision variables. Now, just before getting into the software, I just wanted to show you here, when we worked with our beta users and our customers, it was mentioned that they would like to see up to 3 solutions per optimization configuration. They don't want to just get one answer. And so the way we've handled that is, if I just quickly go back to the slide before, we have different weights that we give these different terms in the objective function to kind of provide a different solution. Could everyone please stay on mute? Thank you. Yeah, so what we do here is we have these 3 different scenarios. One is kind of giving us a balanced result, while the second one defaulted is on quality focus, so giving a higher weight to achieving the targets, while the third scenario gives a highest weight to achieving the cost. And any of these can be changed, renamed, and you can run only one scenario if you choose. Now, we don't give you actual values to put in, it's just the background here and initialization strategies and scaling and things are, of course, ProSensus IP, but we do allow you to make some changes. We also, in the software, provide a best match, so allowing you to determine the closest matching historical formulation based on both the targets that are configured and the objective function values, and then also ensuring that the best matching historical formulation doesn't break constraints. So that would be useful if you're determining for large or unfamiliar data sets, seeing what was kind of the best matching past formulation to what you've configured in your optimization, and also in identifying optimization constraints that may need to be relaxed. So without further ado, here I will go into FormuSense. So here we have FormuSense. Right now I'm in the modeling tab here, and I just wanted to briefly show kind of how easy it is to interpret the models and understand our relationships. You select something on an observed versus predicted plots. You can see it in the raw data plot, like mixing speed, and see it in the score space as well. And then the simulation is quite easy to set up. You can start from a historical experiment, generate that simulation, and view those results. Very straightforward. And then we got to the optimization. So like I said, it takes about 3 minutes to run this optimization for the 3 scenarios in this formulation. And so I've pre-run them. And generally, if you're on WebEx, actually it takes even longer because it's using up resources from your computer. So we've pre-run them for you for this demo. And in this case, the first thing you do is you set your targets. So in this case, you can set either quality targets or score targets. So I've set a quality target for Y1 only here, and we're saying we want Y1 to be 0.9221. And we can see a plot of all the historical values of Y1 from our modeling, were included in our model, and we can see we're kind of pushing to the extreme here with this target. We could also add targets for other variables, but I'm not going to do that in this case. And so that's the target, achieving this quality variable. And then we have various limits. So various bounds and limits for quality. So we have 7 quality variables. And the defaults are that if a quality variable has a target, it puts a defound bound of ±1 standard deviation, but you could click on it and change any of them. If it doesn't have a target, then it's just the data set min and max. Again, any of them could be adjusted. Then we have cost. For cost, the upper limit that we allow the cost is, in this case, defaulted to the 75th percentile, but can again be adjusted. For process conditions, defaulted to data set min and max. Again, can be adjusted. I'm going to skip over the ingredients tab for now. For mixture properties that we had in this data set, we had the global density and the various rubbers.
And reply message
could you please mute Dr. Kaylin?
Reply and sir, kindly let me know available your free time so that I can talk to you, Annie. But
okay, so I'll just continue here for the ingredients. Pardon? Okay, for the ingredients here, the ingredient tab is kind of the most complex. It has a few things in it here. So it's per class. So we have the rubbers, the oils, and the polypropylenes. And the first kind of bound we have is how much of each class can you put in? So how much rubber can the formulation consist of? And it's again defaulted the data set min and max. So here we can have anywhere between 40% and 84% rubber. the number of ingredients to use. So if we plot them historically we see that the formulations are used anywhere between 1, 2, 3, 4, or 5 ingredients, and the default would actually be 5. But because very few of them use 4 and 5 ingredients, I've adjusted that to be 3 in this case. And then here is that minimum percent to use if it's used. So that what that means is we do not allow it to suggest using less than 3% of an ingredient. It can be 0, but if it's used at all, it has to be at least 3%. And then each of the rubbers here, we have the 31 rubbers, 13 historical ones, and then there was that were used in historical formulation, and then 18 new ones. And if you click on them, you can change the bounds. Again, it's default to the minimum that was used in the formulations, and the upper limit is the class upper bound. Anything can be changed, or you can set it to be unavailable, and so on. And then we have our advanced tab. The advanced tab is the balanced, is the 3 scenarios, turning them on or off, renaming them, or changing the weights around. How far we allow the SPE and HD2 to extrapolate, and some optimization tolerance and iteration settings. Now, the way I would usually start with these types of applications is to calculate only the best match. And so what you do there is you're looping through the historical formulations, and you're finding which historical formulation matches best for each of the 3 scenarios. And that's very quick. I'll show you here running that. So that has been run live here, and we see the results screen. So the results screen will vary once we've run an optimization, but when we're running best match only, what we get here is in the metrics tab, we see which was the best matching historical formulation for each of the 3 scenarios, and they're shown here on the plot as well, in the score plot. And it just so turns out in this case they're the same for each of the 3 optimization runs, but that's not always the case, because in some cases the different balance of weights and such will give us a different best matching result. Now what we see is how close we are to that 99% HD2 limit. So the best matching formulation was around 50% of the limit, very, very low in SPE, high in cost. So if anything exceeds any of the bounds you've set, it'll be shown here in red, and we see we've exceeded the bound in cost and kind of the target deviation in terms of numerical values, but also you can see it in the trend here, the standard deviation from the Y target. So this historical best matching formulation is a little lower than the target. We can see what the what the quality was that was predicted for that particular one in a tabular format. We can see the process conditions, the mixture properties, and so on. And we can also see what the ingredient ratios were and what ingredients were used in that formulation. Now to note here, this best matching formulation is touching the upper limit in terms of how much rubber it can use. It uses 84% rubber and very little oil and polypropylene. And we know that rubber is actually the most expensive ingredient in this formulation, in this system, and therefore that's why the cost would be high. And so when I actually go, so this kind of shows me what the constraints are going to be to get a high value of Y1. And so what I'm going to do when I actually run this scenario is, so I have this target here. In the limits here, I've actually relaxed the constraint here on cost, because pretty much if you have it much lower, it's not going to be able to find a solution very well, because we need a high value of, we need a high cost to get to that quality metric. So everything else, I've kept all the other limits the same. In the ingredients, we say 1 to 3 and so on, and I've pre-run this this optimization. Now we have a little exclamation mark here because I've clicked around on things, so it's thinking it's not up to date, but it actually is. So when we go ahead and run this, on optimization, in the metrics tab, we get some more information than we did when we just did the best matching. And what the first thing we get is whether or not each of the 3 optimization scenarios solved successfully. So thankfully, in this case, it did. If not, it would give you a red bar and some kind of error, or not really an error, just saying it didn't solve for the probably over constrained. And then we get a table that shows us a few things about the values of various terms in the objective function. So we see kind of what percentage of the limit we're hitting in terms of SP and HT2. So those are the model validity metrics. Here we see that for the cost one, we're kind of really extrapolating a bit in terms of SPE, but based on the tolerance that we set, the upper bound is 100, and so 100.1 is fine. We see the cost of each formulation. So when we have the balanced scenario, it's at 272. Quality is a little more expensive at 278, and the cost one, it was able to find a cost one that's quite a bit lower at 225. And we also see the deviation from the targets. So you can see here the quality one attempts to get closer in terms of the quality deviation. The balance is kind of balanced, and then the cost gets closer in terms of cost, of course. In the score space, we see the quality, solution, and balance is quite similar, but cost is kind of sitting over here. And we can also see a plot of how that Y quality variable is fit from the target. And we can also look at it in terms of the raw data plots. So on the raw data plots, we see the bounds for that Y1 variable, the target, and where we've landed. And we can scroll through all of the variables. So the ones without targets don't have that green line, but they still show where you're touching bounds and things like this. And can also look through the X data and the various bounds and so on. It shows you as well how it compares to the best matching in terms of the objective function kind of values and where it's improved. So generally what you'll see here is here for the balanced one, you see that the HT2 value is 73%, whereas the historical formulation was a little closer. So generally to achieve an optimization, we do extrapolate a bit more in terms of SP and HT2, but stay within the model 99% limit. But the cost and the target deviation generally tend to go down as we minimize those things. We can also take a look at tabular values of the quality that's predicted, see where we might be touching bounds and so on, and compare to the best matching again. Process conditions are similar, shows you what those are, mixture properties that are calculated, and tabular values of the scores in here as well. And then we get to see the formulation, which is usually the most interesting part. So for balanced, you see we used rubber 1 and rubber 12, and oil 1 and polypropylene 1. To get the quality one, we get 50% of rubber 1. We also use rubber 12, but we use 7.5% of a new rubber. So that's interesting. And then the cost one uses rubber 1, new rubber 1, and rubber 8. So they don't use more than 3 rubbers each, but they use a different combination. And even then they get similar quality metrics. So that gives the user some idea of what they might want to try, either as experiment or so on. One last thing I wanted to mention with this one is that, I'll just go back to this Y data plot, is that optimization is sometimes can be a little bit iterative if you take a look at this and say, okay, I'm not really happy with the fact that we didn't get close enough to our target. So you can go in and add, maybe increase the lower bound or give it more importance or something like that in the setup. So you could go here and give an importance of high, and in the limits, you could go in and adjust the lower bound of the quality such that you would maybe get closer. Okay, so, and then one last little use case would be the score targets. Here we would say, how would we get to a particular area in the score plot if we wanted to run an experiment that gets us maybe here for a DOE or something like that. So we can go in, I've already pre-configured that one as well. In the setup, we can target -2 and 1. And then we have all the same options for limits. The only thing that changes is that we can't set quality limits in this case, the target limits only. And then we would go through and run that one and see the results. And the main differences here would be that we would have a location for the target in the score plot, and we can see kind of how close we got in the various scenarios. And again, everything else is similar, and we can see, you know, what the combination of formulations we are to get there, to get to that area of the score spot. And it's quite interesting that you can run quite a few different combinations of ingredients and get to the same area of the score plot with kind of minimal cost and so on. So yeah, I think I should go back to slides now and open it up to questions. So we're nearing the end. And so just one last slide here before we open it up. So of course, ProSensus offers both software licenses and consulting services. And we highly recommend that you download the trial and activate that. And then we'll email you the tutorial data set and slide deck to get started. It's an annual subscription license and so on. And the last thing I just wanted to mention is that optimization is not included in the standard 30-day trial because we really let anyone on the internet download the trial, but we're more selective as to who we give the 7-day optimization trial to. So that would be on request, and you can email me or Kristen. So thanks very much. I will see if there's any questions. Pardon? We'll stop recording.